Hey, welcome back to Real Analysis. We're going to continue our work in Chapter 7 on the derivative, still looking at some familiar differentiation rules that you were exposed to in your first semester of calculus. This section, 7.3, well, in the second subsection of it rather, 7.3.2, we're going to talk about the chain rule. Okay, so that's our goal, is to establish this familiar differentiation formula that you learned in calculus when you're evaluating the derivative of a composition of two functions. Typically in calculus, students call f the inside function and g the outside function, because g goes second. You take g of f of x. In calculus, you learned that in order to differentiate such a thing, you take the derivative of g, that is the derivative of the outside, evaluated at the inside function, and you have to multiply that by the derivative of the inside function. All right, so this is a familiar rule. Like in the previous section, and throughout the entire chapter, really, our goal here is not to illustrate the applications or the computations with these rules. I mean, that's literally what you did in your calculus sequence. So our goal here rather is to establish rigorously the validity of these things. So we have these definitions of limits of functions, we have definitions of derivatives. This is an equation that says that a couple of derivatives are equal to each other, or a derivative of something is given by some expression, rather more precisely. So that's our goal, is to establish that. All right. If we proceeded like we did in the previous section, we would kind of look at a product. You can kind of see by the virtue of the formula, we'd look at the product of a couple of difference quotients because I got a G prime and an F prime, but we'll run into trouble because that one of those difference quotients might keep taking on the value 0 in the denominator, even though our input isn't taking on the same value as where we're taking the limit. All right, so that sounds a little bit abstract, but we're going to kind of dodge that. We're going to take a different approach than what the book does. We're going to start with some result. It's going to be useful in proving the chain rule because it kind of gets around the notion of having to look at the denominator when you look at the difference quotient to take a derivative. Okay, it's also going to be a useful result in the next section when we talk about the inverse of invertible functions. And this is a standard approach. Our book doesn't take it. It's kind of relegated to the exercises, but it is a standard approach in this business. So that let's see what it says. So the result that I'm talking about is called Carathéodory's theorem. Carathéodory is a person's name, a Greek mathematician. And so what does Carathéodory's theorem say? It's basically an equivalence. It's a characterization of what it means for a function to be differentiable. All right. So a lot of the statement of the theorem is just kind of preamble. I've got an interval I and a point in it, right? Every point of an interval is a accumulation point of that interval, and I've got some function on I. So that's the preamble. I've got a function defined on an interval. I pick a point in the interval, and then it's a characterization of differentiability. It's a condition that's saying this function g, it's differentiable if and only if this other condition holds. And the other condition is there's some other function. It's called phi in the notation of the statement that I'm giving. Phi is defined also on I, and it's continuous at x0, and it satisfies this equation. I'm going to highlight this equation. You should pause the video and write it down. I'm going to refer to it a lot below, and I'll just refer to it as equation 1. But this continuous function phi multiplied by the change in x, right? So when you multiply phi by x minus x naught, you always get the change in g. So Carathéodory is saying that if such a function phi exists, then this function g is differentiable, and vice versa. If g is differentiable, this function phi exists, and in that case, the value of phi at x0 is the derivative. And I think you can kind of see it. If you just divide both sides by x minus x0, well, that's the difference quotient. So if x isn't x0, this function phi kind of equals that difference quotient. So this is just really sort of a pretty gentle rephrasing of what it means to be differentiable, but it's nice because the green highlighted formula here doesn't have any fractions in it. I don't mind if something is 0 in that equation because I'm not dividing by anything. Okay, so let's see if we can't give the proof. You've written down equation 1. I'm going to refer to it. I'll just call it the kind of Carathéodory equation, or equation 1 for short here. It's an if and only if proof. So let's start off in the direction that I'm supposing g is differentiable. Okay, so suppose I've got this differentiable function at this point x naught in my interval. Well, that means that the derivative g prime of x naught exists. Okay, So how to define phi? Well, I'm going to define phi like this. I'm going to say for any x in I, it's piecewise defined. Phi of x, if you're not x0, if you pick a point other than x0, phi of x is the difference quotient. I'm cooking it up for that equation 1 to hold. This is a perfectly well-defined mathematical expression if x isn't x0, okay? If x is x0, then I just say phi of x is g prime of x naught, all right? So that defines a function phi on all of I, because if you pick a point in I, it's either x naught or it's not. And in either case, I know how to compute the output of phi, okay? So how do I prove that this function phi is continuous? That's one of the things that I'm supposed to show you is this function phi is continuous. Well, I'm going to use the definition of continuity. So what do I mean by that? I'm going to take the x, I've already remarked that x naught is an accumulation point. I've written that down here. It's an accumulation point, so I can speak about continuity in terms of limits. Okay, so I'm just going to take the limit of phi as x goes to x naught. And that limit doesn't depend on the value of phi at x naught, so I can replace phi of x with what it equals when x is not equal to x naught, because this limit never depends on the point that I'm taking the limit at, right? So I replace phi of x with this difference quotient, I'm going to call it, g of x minus g of x naught over x minus x naught. And well, g is differentiable, so that limit by definition is g prime of x naught, which we said by the definition of phi is phi of x naught. All right, so that proves that phi is continuous. Its limit exists at x naught, and it's got the right function value. So by definition 533, g is continuous. How do I show that equation 1 holds above? Well, we'll just kind of check it out. If you take x to be x naught, stop the video or you wrote it down, both sides of equation 1 are equal to 0, right? G of x naught minus g of x naught is 0. Phi of x naught times x minus x naught is 0. If x isn't x naught, and you pick some element in I, then by the definition of phi, maybe I can sort of scroll back. Well, you can scroll back and look at it. By the definition of phi, we said phi is this difference quotient. So multiply both sides of that by x minus x naught, and you get equation 1. Cool. So there's half our proof. If g is differentiable, this continuous function phi exists, okay, and it satisfies equation 1. So now we have to prove the converse. So now we're going to suppose that I've got this function phi, okay? I'm going to suppose that it's continuous at x naught and satisfies that Theodore equation up there. And then my goal is to show that phi is differentiable and that its derivative at x naught is equal to phi of x naught. Okay, well, if you take some point in the interval that's not equal to x naught, divide both sides of equation 1 above, the Theodore equation, by x minus x naught, and we get that phi is equal to that expression. Okay, phi is a continuous function. X naught is an accumulation point of the interval. So if I take the limit as x goes to x naught of phi, I know I have to get the value there. That's because phi is continuous. I'm using the limit definition of continuity, which is valid at an accumulation point. Okay, but by this equation up here, that limit as x goes to x naught of phi is equal to the limit of the difference quotient. Okay, so the limit of the difference quotient exists, so that precisely means phi is differentiable. Differentiable means that this limit exists, differentiable at x naught. And moreover, what does that limit equal? That limit equals the value of the derivative at x naught by definition, but it also equals phi of x naught, and so we get that equality. Okay, so not a deep theorem, Theodore. It's a very useful way of kind of just rephrasing what it means to be differentiable at a point. It means that the change in your outputs is some continuous at that point function phi times the change in the inputs. And phi's value at x naught is the value of the derivative. So it talks about differentiability without having to deal with fractions. Okay. So you can stop and let that kind of sink in. I'm just going to continue on here. So back to our chain rule discussion. Remember, we want to show this familiar looking differentiation formula from calculus. So if we were going to proceed like we did for the previous rules, what do I mean the previous rules? You know, the sum, product, quotient rule. We'd basically look at the difference quotient for the composition, right? we'd look at g composed with f of x minus g composed with f of x naught, and we'd divide it by x naught. And it wouldn't take us very long to kind of think like, well, especially taking our clue from what the chain rule says, we'd kind of multiply and divide that expression by the change in f of x minus f of x naught. Because this first factor here, well, this kind of looks like g composed with f prime, the limit of it anyway. This thing over here looks like f prime. And the product of those two things looks like, the first one looks like g prime at f of x, because it's g of f minus g of f of x naught. The second thing looks like f prime. So their product looks like what the chain rule is supposed to be telling us. But there's a little bit of a difficulty. It can be worked around. Your book actually gives a proof, well, by cases. And one of the cases, you're kind of left to look at the details in one of the exercises. I encourage you to do it. It's certainly within your grasp. But the problem with this approach is that as x approaches x naught, even if we always insist that it's not equal to x naught, so we're not dividing by 0, this expression, f of x minus f of x naught, might keep taking on the value 0. So it's not impossible that in every single punctured neighborhood of x naught, f of x minus f of x naught might be 0 for some x. All right, so it means that this expression that I'm trying to take the limit of isn't really going to be defined in any neighborhood of x naught. And that's going to require a workaround. Your book suggests how to work around it. It kind of, the proof of the chain rule in your book is two cases. Case one is what I'm talking about doesn't happen. All right, so you just take the limit of both sides of this equation that we're looking at in the center of the screen and you're done. And case two is it does keep happening, that in every single punctured neighborhood of x naught, there's an x that makes this expression that I'm underlining equal to 0. Well, you can check out the exercise. The exercise basically says in that case, f prime has to be 0, in which case both sides of the chain rule give 0. So you can certainly do it this way. But I'm going to propose that we do another workaround. We're going to use Theodore's theorem. Theodore's theorem lets us get at differentiability without having to divide. So that's the approach we're going to take here in this video lecture. Okay, so let's get her done here. And I state the chain rule precisely. Before I just kind of wrote the formula, but here's kind of the preamble for it. So it's about composition. So I'm going to take two intervals, call them I and j, and then I've got a function g on I, and f is defined on j. So I and j are just the domains of the two functions, f and g. And the composition has to make sense, okay? So when I take some number in the domain of f, and I plug it into f, I need to get something in the domain of g, right? So what I highlighted in yellow is only designed so that the function g of f of x makes sense. Every output of f is an input for g. Okay, so that's all that means. And then I pick some point, x naught, in the domain of j. Okay, so what are the hypotheses? The hypotheses say that if you can differentiate f at x naught, and you can differentiate g at f of x naught, then you can differentiate the composition at x naught, and the formula for the derivatives is given by that chain rule formula. So here I'm doing it point by point. The overall formula will write just like usual. If it's true for all x naughts in the interval j, well, then we'll just write the formula in terms of the variable x, like usual. Okay. So in a nutshell, what did I write here out very precisely? That the composition of two differentiable functions is differentiable, and the derivative works like that chain rule formula. Okay, so how to get this done? Well, I'm going to just keep using Theodore's theorem. 2 times in the proof, I will use it in the direction that I know something is differentiable, so I get that equation, that green equation 1. The last time I use it, I'll know that the green equation 1 holds, and so I'll be able to say something is differentiable, and I'll even know what its derivative is. Okay, so maybe it's a good exercise for you to kind of delineate every time I use it in this proof. Okay, so using the notation above, I won't recapitulate and quantify everything in the statement. We're assuming that f is differentiable at x naught. So f prime of x naught exists. And here's our first application of Theodore's theorem. I'll kind of enumerate it the first time we're using it. And I'm using it in the direction that I know f is differentiable. So there has to be some continuous function phi. Oops, wrong pen. There has to be some continuous function phi on the same interval f is defined. It's continuous at x naught. And here is the Theodore equation. All right, I highlighted it in green above. Maybe I'll underline it in green here. So what does it mean? The change in f is this function phi times the change in x. That's true for all x and j. And the derivative f prime at x naught is equal to phi of x naught. All right, so that's our first application of the Theodore's theorem applied to the differentiable function f. Okay, now I'm going to apply it again. Try to leave this visible here. I'm going to apply it again. I'll highlight it in a different color. G is differentiable at f of x naught. So g of f of x naught exists. So a second application of Theodore's theorem. It's the second time I'm applying it, but I'm applying it to the function g at the point f of x naught. So the second application of it says there's some other function. I can't call it phi again, so I'm going to call it psi. It's defined on the same interval that g is. Psi is continuous at f of x naught, which I'm going to just denote by shorthand y naught. Okay. And the Theodore equation holds that the difference in g's is psi times the difference in the y's. So this again is by the equation 1 up there, highlighted in green at the top of the lecture. I'll underline it in green here. That's true for every y in the interval that g is defined on. And moreover, we know that the derivative of g at f of x naught, that is g at y naught, is the function value psi at y naught, f of x naught. Okay, so there's our two applications of the Theodore's theorem, one applied to the differentiable function f, one applied to the differentiable function g. Good. Okay, now we're going to do a little bit of algebra and stitch that together. If we stitch all of that stuff together, you'll have to maybe go back in the video. I didn't fit it all on one screen here, but if we plug all that in, well, we said above in blue, I can try to use the same kind of highlighting scheme here. We said that g of y, well, I'm writing that as g of f of x, minus g of y naught, I'm writing that as g of f of x naught, was psi of y is f of x, times the change in y's. Well, the y's are f of x's. Okay. But now we said that the change in f's were given by phi times the change in x's. So I'm just substituting what I highlighted in yellow there. So if I kind of roll all that together, and maybe I won't highlight it because the highlighting scheme maybe is getting confusing, but g of f of x, well, that's just g composed with f. So I've got g composed with f of x minus g composed with f of x naught is on the right-hand side of this thing. What have I got? I've got psi composed with f times phi evaluated at x, okay? So this part right here, psi composed with f times phi, I'm just writing it in function notation, times the change in x, and that's true for all x and j. Okay, but let's think about this. F is a differentiable function. So it's continuous. I think that's theorem 7.6. Phi is continuous, psi is continuous and phi is continuous. Compositions of continuous functions and products of continuous functions are continuous. That's these chapter 5 theorems. You'll have to look which one's which. One of them is about products. I would guess it's the earlier one, 540. One of them is about compositions. 543 is my guess. So that thing highlighted in yellow down here, I'm underlining it. It's made out of continuous functions at x naught. It's continuous at x naught by our theory. Okay, so you see where I'm going? I've got the difference of this composition is a continuous function times the change in the inputs. So one more thing I need to check, and then I can use Theodore in the other way. I have to check that this continuous function's value at x naught is equal to this formula that I want to write, okay? So if I evaluate that continuous function, psi composed with f times phi at x naught, just plugging in, I get psi of f of x naught times phi, but we already wrote above that psi of f of x naught is g prime, phi of x naught is f prime. So it's my third and final application of the Theodore's theorem. It's the third time I'm using it, but I'm using it in the other direction now. I've got this function psi composed with f times phi satisfies the Theodore equation, right? And it's continuous. So one, I know that g composed with f is differentiable. It's one conclusion. And moreover, the value of that continuous function at x naught is the derivative. So I know that g composed with f's derivative is the value of this continuous function at x naught. We just worked out what that value is. Okay, so if you look at these two things at the extremes of the equation, that's the chain rule. Nice. So once again, we did that for 1 point x naught, but if all of those hypotheses hold for every x naught in the interval j, then g composed with f is and g is differentiable at every point in the interval I, then the composition is differentiable at every point in j, and we get that formula in terms of x. Nice. Here's just a real quick example to end on. We've already derived this formula with the product rule, but I wanted to bring it up again. If I take g to be the power function, so g of y is just y to the n's a natural number. It's differentiable. One of your homework assignments, you're going to prove by induction that g prime of y is that familiar power rule. Okay, so if you take any other differentiable function f and you compose them, g composed with f, well, the chain rule says that the derivative of that is just g prime of f of x times f prime of x. That's by the chain rule. But g composed with f, if you plug f into the g to the n function, then you just get f to the n. So this g composed with f prime, that's just f raised to the nth power prime. Yeah, composing something with a power function is taking the power of it. So we get this formula that the derivative of f to the n is n times f to the n minus 1. That's your outside function evaluated at your inside times f prime of x. Okay, so sometimes in calculus books, they'll call this something like the general power rule. So you can take powers of not just x to the n, but any function to the n, right? So you've seen examples like this, like if you wanted to say differentiate something like sine to the seventh. Sine to the seventh is the composition of the sine function with the seventh power. So the differentiation formula goes, well, it's 7 times sine to the sixth, and then you need to multiply by the derivative of sine, which we certainly haven't proved here, but you know from calculus that it's cosine. So there's sort of a specific example. Okay, so that's it for this video. Thanks for listening.